60 FPS. What a loser. Shut the fuck up. Okay, I will shut the fuck up. So, I want use you to wash my hands. Chuck. Not from you. Um, that's not good. It's not some good spelling. What? Hello? Hello?
Hey Chris, how are you?
I'm good.
Okay, seems to have we had a problem with the connection, I think. I must have been. You were always online, right?
Uh, I think I'm on the website of the Skype, but I think when I search to other windows, then it doesn't.
Okay. Yeah, it was. Yeah, okay. That only started ringing. Yeah, it was okay. No problem. Because I was thinking, something with the connection. Okay, all right. Um, just let's go. And we said we will continue with some questions, right? We still have from the actually several papers we can choose from. Work on it. And but I would say maybe half the hour max, roughly, we're going to use for the questions, and then we continue with the superposition of waves. Huh? Okay, so because obviously the Skype has changed a bit in appearances, that's for sure. Okay, now I want to do that one. Okay, I think question 4 is an interesting one. And it's the diameter of a nucleus and the wavelength of an electromagnetic wave are in the same order of magnitude. When you look at that sentence, what does that mean?
Uh,
This first sentence here, what does it really mean in practical terms?
they have this. They have similar scale of uh, size.
Yeah, exactly. And when we talk about size, which two sizes would we talk about from the nucleus and the wave?
Wave would be length.
Okay, yeah, okay. And for the nucleus?
Uh, Diameter.
diameter, which in the end is length as well, right? Actually, so that's why this will be very important, because that's of course kind of very useful to measure actually the sizes of nucleus. Otherwise, we would not really know. But thanks to these well phenomena, kind of, or the different types of waves, we can actually do that. And now, in which region of the electromagnetic spectrum would that occur? Meaning, in other words, which type of waves would we intend to use in order to measure the size of a nucleus?
I think gamma ray.
Okay, and why would we say that? To prove your point in terms of dimensioning. What can you say something about the dimensions?
Huh?
When we said about the magnitude, right? So somehow when we say gamma ray, why would they fit? So
Because gamma ray is 10 to the power negative 10 to 10 to the power negative 16.
okay, yep. And the diameter of a nucleus, or hydrogen to be precise, for example, because of course they vary.
I'm not sure.
Okay, yeah, that's fine. So I mean, so hydrogen would be 1.76 times 10 to the power of minus 16, 15, excuse me, minus 15, and of course meters. So that, of course, that's just one. So obviously we talk about an extremely simple nucleus, just one proton actually, and the more protons we add, meaning even if you go to oxygen, we already talk about 8 and 8, so 8 protons, 8 neutrons. So they must have quite a bit of a larger size. And of course, the best one, just linking it quickly to chemistry, is when we go down, of course, right, in the periods, then you have more shells. So basically, more or less, although, of course, they grow along the period, the group as well, because they're adding neutrons and protons, but in tendency, the way they are arranged, you can, as a first indicator, go by shells, kind of, gives you an indicator, which then gives you the larger diameter of the molecule. And then, of course, when we talk about nucleus, do we talk about the whole atom or just proton, neutron? That's sometimes a bit misleading too. Huh? Okay. Now, when we look into question 5, we have sources. One is infrared and one is ultraviolet. And it's so suggests the wavelength. And we want to know which ones are, or which combination is correct.
Infrared is 0. I mean, 7. No, 4 times 10 to power of negative 7.
Okay.
To 10 to the power negative 5. I mean, negative 3.
Mm-hmm.
So it's the bottom 2.
Okay. We mean D.
Huh?
And you say bottom 2. Would that be C or D?
Yeah.
Which one?
I'm saying either because ultraviolet is seven times 10 to the power negative 7 to 10 to the power negative 8.
Yeah. I mean, in this discussion, in tendency, it's usually the powers which count, right? And of course, the range. So that makes it a bit more tricky because we know there are not just one precise And in magnitudes, they vary as well a bit. But of course, in such a table, then we have to, yeah, focus on the numbers which are at on display. So -8, okay. So let's say this one, theoretically this one, put it in brackets. And what about the infrared?
C.
C, right? So 10 to the power -5. Okay, so C. All right. Gamma ray. I think that's a similar question. Yeah, maybe 7. This is very typical, right? Because when we talk about telescopes, we are quite often not talking about just visible light. We would only see a small part of the universe ultimately, because there are many other waves, which gives us very good information about what happens in some parts, galaxies, planets, stars, etc. They are not just well, stars which have been, so they or which will form. They are not stars yet, or have been stars. So there's some remains. That will give us important information as well. So now, when we talk about a radiation with a wavelength of 2 centimeters, so which type of telescope should we choose?
Uh, Microwave telescope.
2 centimeters. When we think of the wavelength for 2 centimeters, that's how much?
Microwave.
Mm, or so it's 0.02 meters, right? So something like 2 times 10 to the power of -2. So when we see something like with such a small wavelength, it's well, it's still in which realm would we say it should be?
This microwave is 10 to the power -3 to 10 to the power -1.
And visible light, as of an optical telescope.
It's 7 times 10 to the power -7 to 4 times 10 to the power -7.
Okay, huh? All right, okay. I mean, it's just to, I mean, well, or in other words, if we see a very small wavelength, what does that tell us? Or very short, actually, is the better term. Or we could say a sense that the shorter the wavelength, what could we then add to that sentence?
The higher the frequency.
Yeah, exactly. Huh? Yeah, that's always a good thing to think about, right? And 2 centimeters is obviously already comparatively short. Visible light, like you said, is interestingly much shorter, but hence much lower frequency. Huh? Okay, good. So in this case, so we would have microwave. So that means somewhere out in the universe, there's a star or a previous star which emits microwaves actually for various reasons. Huh? Okay, so it's not just a visible one. This one is on the hard level, it says. Let's see. Did you do any of those questions, Chris, eventually?
I didn't have time.
No, that's fine. I'm just asking because otherwise you can say, well, let's do those. You would say, I would rather like to because I'm not so clear or whatever. No, that's fine. Of course. Okay, so this one is a bit more complicated. And it gives us the value of the ratio. Well, maybe it's not that complicated, but at first it seems to be eventually. So what kind of transformations do we have to do? It's in its core. Well, it's a mix between physics and, but ultimately more math than physics, kind of.
Because they both have the speed of light.
Mm-hmm.
So
Okay. Yep.
30 times 10 to the power negative 6 times frequency of infrared equals to 400 times 10 to the power negative 12
Okay.
and times the frequency of X-ray.
Okay. So okay, let me see how. So you want to say times frequency, right, of X-ray? Is that okay? Or 30 times 10 to the power of minus 6 is which one? Which wavelength? Frequency?
Infrared.
Infrared, huh? Okay. And and that is equal to what?
Equal to 400 times 10 to the power negative.
Okay, sorry, my bad. I wanted to ask, well, what is the which equation are you looking at? Just the basics.
It equals to the speed of light.
Yeah, exactly, right. So what we can do, and then henceforth, as we said, C infrared, of course, is C UV, X-ray. Sorry, X-ray, X-ray. So, I mean, of course, it's the same, you know that, but it helps us to think because when we set these two equations equal, so of course we can say, well, this is the same as what? Because both are equal to the speed of light, right? So I can obviously equalize the two equations. And what is the second equation, the one for X-ray, in terms of numbers?
400 times 10 to the power negative 12.
Negative 12, okay, very good, times frequency of X-ray, right? Is C as well. Henceforth, because the reason why I make it like that is obviously we want to know the ratio, right? So the easiest way in such a case, of course, it may come to you as well and instantly make the respective ratio anyway. But if we strictly speaking, so we can say, well, obviously um, they are equal to each other, so I can divide one by the other, so to speak, and henceforth, or I can just make the ratio. Depends on how I look at it, and because I want to know X-ray over infrared, huh? So I make the FXR over the FIR, IR, and that would be in values. What would that be? I mean, which two values do I have to list?
Um, it will be 30 times 10 to the power of negative
Okay,
6
yeah.
over 400 times 10 to the power negative 12.
Yep. Huh? Okay, and that is how much without calculator?
Uh, 30 over 400 times 10 to the power of 6.
Okay, good one. And then in order to simplify it further,
Uh, 3 over 4 times 10 to the power of 5.
okay, yeah. What I would do, Chris, in that context is make it, what we can do easily with is to say, well, 30 divided by 4. This is something I can easily calculate, right?
Oh, yeah.
Right, then so I just move so make it 10 to the power of 4. And so, of course, and 30 divided by 4 is how much?
7.5.
Yeah, exactly right. So I mean, this is something if you would have to calculate it without calculator, then bring it as close as possible to what we are very familiar with, something like 30 divided by 4. Of course, can as well make 300 divided by 40, of course, but typically we are a bit more familiar with in the below 100 range, usually. And then, of course, you can just apply that for the powers. Huh? Okay, all right, that was more about this one. But ratios are always something which is showing up very often, as we've seen now in the meantime. A lot of questions include ratios. And question 2, well, this is actually a simple comparison. It could be a bit more complicated questions. I think we leave that because you just have to compare, obviously, what has been transmitted in terms of ratio, right? Obviously, the percentage-wise, that's missing. Actually, that's not so good, right? That should be percentage, actually, just to be very precise, because that's what you have to be. This is a bit it's okay, right, to have from meter to millimeter to micro, nano, but basically it would be, of course, better to have meters, maybe to the power of something, could be, right, maybe to the power of 2, and then everything else is then just accordingly. So it's usually not a good idea to make such a table. Of course, this is the purpose here, so make life a bit more complicated for the sake of the exercise. But to tell you is it has to be complete, even if it's out of the text. What is the range, the percentage of transmitted wavelength? Yeah, then percentage, please to list here, and to have then various units of measurement. I mean, in terms of dimensions, is a bad idea under normal circumstances. It should be more something like this, or of course without that one as well. Then we can still do the accordingly. Huh? So, but we heard that we don't go. It's just a simple mix and match question, actually. This one is a bit different when you look at the monochromatic light. When we talk about double slit, that's something we cover actually further today. But for this purpose, it's okay because we talk about a double slit. We have a distance between the slits, and I think we wait with this one. We could do it, but we have not really talked about the slit equation. So let's leave that for the time being. I don't know why that slid in here actually, because this is a superposition question ultimately. But nevertheless, what does monochromatic mean?
Only one light, one color light.
Okay, so is a natural light monochromatic?
No.
Right, exactly. What could be something we still see, also visible light, but monochromatic? What would that typically be? Can you think of one?
A part of a rainbow.
Okay, yeah, that's an interesting one. When you think of, think of kind of, well, for us at least on Earth, artificially generated light. Of course, in the universe, we can see that as well anyway. But, and it's a standard feature in any science fiction movie, basically. What type of ray would that be, which we can still see, but is monochromatic? And it goes towards what you said with the rainbow, kind of. But just think that you would only see one, right? But you say one part of the rainbow.
The laser.
Laser, exactly, right? That's the beauty of the laser. That's why it's so massively used in physics, because it's able to generate, well, just one wavelength, for example, or one frequency, whatever, right? And that makes, of course, it very interesting to conduct experiments, because if you have multiple Well, frequencies, it will be a hell of a lot of more difficult to make a proper experiment. So that's one thing. The other one is nowadays, of course, or in the meantime, for the last 50 years roughly, we can do a lot with lasers on top of that. I mean, like for various purposes actually, so independent of such physical experiments. Huh? Okay, now let's see quickly if you have something in the polarization which would be of interest. And talk about, sorry, medium question. That was wrong, sorry, my bad. So it's something we actually more or less discussed last time, and we only have one polarization, or the beam has an intensity already. So what is the intensity of the transmitted beam? So we are going backwards, so to speak. So which equation are we going to use?
The intensity times cosine squared theta.
Okay, yep. Yeah, that should have been like that and like this. Huh? So which one is which now? Which one do we want to know?
We want to know the new intensity.
Okay, all right. So standard procedure, huh? Okay, so what do we get, Hensworth?
16 times cosine squared 45.
Okay, and
Be
what is the cos of 45?
cosine squared of 45 is 0.5.
Do you remember the table, Chris,
Uh,
with the trigonometric values, if you want to say so, for cos and sine? Because it's a common one that very often students say for 45 half. Somehow, because 45 is between 0 and 90, so it's understandable, but it's not. However, sine and cosine, of course, are the same because they are in the half of 90 degrees, as a halfway through between 0 and 90, but that doesn't make the cos or the sine half. Unless you already said, of course, the square. Sorry, maybe did you mean the square or the cos only?
the squared.
Ah, okay, then my bad. All right, okay. Sorry. I thought I heard you say cos. Or I asked for cos. So that's why. Okay, yeah, exactly. Yeah, no, of course. Then that's completely correct. So 16 times half, because it's one square root of 2 divided by 2, right? And then squared. Okay, so we obviously get 8. Hence question D. Huh? So that's crystal clear. That's good. But that's a bit different. Let's do that one. Because we have to combine answers and see which one is correct of the combinations. Makes it a bit more tricky. So what type of challenge do we face here? What is the basic situation? It's a bit complicated explained, of course. But what is the core of the question basically when we think of polarized light, or any light actually in this case? Do you have any ideas, Chris?
I didn't understand the question.
Okay, yeah, that's fair enough, actually. I read it a couple of times. So first we have the source, huh? So it's unpolarized light, standard I0, right? Okay. Then it goes through a polarizer with a vertical transmission axis. So we have the source, it comes. So how do I imagine the transmission, the polarizer? It has a vertical transmission axis.
Oh, vertical slit.
Yeah. So, and so that's a polarizer, right? Okay, polarizer. And then it goes on to a sheet of material X, which is incident. What does that mean? Or does it even have a specific meaning? Or is it just to say it lands on? So yeah.
Oh, so it goes through the second one.
Goes through the second one as well. Huh? So, and actually, this is now we don't know because it's just incident, right? So it doesn't really specify it. So we have actually a variety of possibilities, right? And it tells us that at the end of it, it's I half, so I0 half. Huh? So it's half. So Hainsworth, what does we start with the polarizer. And actually, well, we know it because of the result, but what does it tell us?
It's not horizontal.
So what does the polarizer have? Because we have two choices, right? So it's not horizontal, I agree. No? So Hainsworth, it must be one, right?
Yeah, and also maybe 3.
Okay. So the first, exactly. So the exactly. Well, that's a good one. So it there's because the point it plays here is with that we say, well, if it's landing, it's, or in other words, if it goes through with the original value, because here it will come up with well, and the respect.